Hello everyone, I am Moin, a first-year PhD candidate at Monash University in Melbourne, and this is a presentation of one of my latest projects which I prepared for Machine Learning Summer School 2020. I will be presenting adversarial graph embeddings for fair influence maximization over social networks, which is in proceeding of ICHCAI 2020. Influence maximization on social networks is a widely studied problem in network science due to its high impacts and applications in various fields such as viral marketing, information propagation, vaccination, social recommendation, and etc. To briefly explain the problem of influence maximization, consider this network where each node represents an individual and the link between a pair shows an existing relation or interaction based on the type of the network. For example, the friendship connection in a social network like Facebook. Now assume we want to diffuse an information in this network by just informing an initial set of individuals. For example, these orange nodes in this figure. And these nodes propagate the information in network by sending it through their connections. So at first step, we select the initial seed and influence them, and from then at each step, each influenced node can pass the information to its neighbors and so on and so forth. And at the end, we have all these influenced nodes in the entire network. In summary, the goal in this problem is to achieve the maximum possible number of influence nodes while only targeting a small initial set of individuals, and the aim is to detect this initial seed set. Although finding the best seeds is an NP-hard problem, recently numerous approximations and heuristic methods have been proposed. However, this issue that whether the final set of influence nodes is fair or not with respect to its sensitive attributes such as race or gender is overlooked. Here we address fair influence maximization, aiming to reach minorities more equitably. For example, this is not a fair system here since men are relatively more influenced than women. Now to address this problem, we aim to apply an embedding technique which can give us highly similar distribution of nodes for our two communities in the new space while preserving the structural properties of the network. To give an intuition why we used this approach, remember that we wanted to satisfy the fairness condition. It means, given two separate communities, we want to influence same fraction of users in both groups. It translates to this equation in the embedding space. Here, I is an influence node in the original network. Capital Z is the embedding space. Pi of Z shows the probability of Z being influenced in the embedding space, and P of Z given I in A is the distribution of nodes of community A in the embedding space. The same is true for the right-hand side and for the community B. To satisfy this relation, it is sufficient that the distributions of communities A and B in the embedding space are the same. So, generally, our approach is to introduce an adversarial graph embedding framework where we co-train an autoencoder for graph embedding and a discriminator to discern sensitive attributes. This leads to embedding, which are similarly distributed across sensitive attributes, and you can compare it with a solo autoencoder framework. And the final outcomes show the difference between the distribution of nodes here. You can see how the distribution of nodes is much more similar in the right-hand side figure. Now in the embedding space, we choose our initial seed set as cluster centroids from the k-means algorithm and use these nodes in the original network to track the influence nodes at each step using independent cascade model for information diffusion. Now let's take a look at our findings. While there are typically trade-offs between fairness and influence maximization objectives, our experiments on synthetic and real-world datasets show that our approach dramatically reduces disparity while remaining competitive with state-of-the-art approaches or techniques for influence maximization. Here the dark blue bars show the fraction of influence nodes in different communities in our method, and you can see how the disparity is reduced while the total influence nodes are maximized. So just to recap very briefly, first, we use an embedding approach to address the influence maximization problem. Secondly, we introduce adversarial network embedding approach for the problem of fair influence maximization. We obtain embeddings which are similarly distributed across sensitive attributes. And at last, our method also achieves high performance in the context of fair influence maximization. Thank you very much for your attention, and for more details, please check out our paper at the following links.